In this video, we will learn about zero polynomial functions and how to find them. Recall that a real number alpha is called zero of a polynomial function f of x if f of alpha is zero, meaning that when you evaluate f at alpha, you will get zero. A real number alpha is zero of f of x if and only if x minus alpha is a factor of f of x, meaning that f of x is actually the product of x minus alpha and g of x for some polynomial function gx. We already seen that in the video about polynomial functions. And also recall that a polynomial function of degree n had at most n zeros. A very important thing that we need to know about polynomial functions are the zeros of polynomial functions. But finding zero of a polynomial function is extremely complicated. However, in some specific situation, we might have various techniques to determine the zeros of some typical polynomial functions. So first of all, we discuss about bounds on zeros. Remember that a polynomial function of a given degree has only a finite number of zeros. So actually, there's upper and lower bounds on zeros of a polynomial function. So the first thing that we talk about is the Cauchy bound of polynomial functions. It is determined by the coefficients of the polynomial functions itself. So given a polynomial function f(x) with coefficient a n, n minus 1, etc. a 0, then denote by m the number 1 plus the quotient between the maximum number of coefficients of the absolute value of coefficient a0 up to a n minus 1 over the absolute value of the leading coefficient an. Then actually all the zeros of f lie in the interval minus m and m. So for example, with fx is equal to 2 times x power 4 plus 4 times x power 3 minus x squared minus 6 times x minus 3, then using the formula above, we can easily see that in this case, all the zeros of f lie in the interval minus 4 and 4. Okay, so that is how you can define the Cauchy bound of a polynomial function. Now we can talk a little bit more about upper and lower bounds of functions. Let's take a look at the first example where f(x) equal to x cubed plus x squared plus xn plus 1. Now for such a function, if you evaluate f at a positive real number a, then you can easily see that fa is always positive, meaning that if alpha want to be the 0 of f, then alpha should be less than or equal to 0. Okay, so this can be generalized to give a criterion for polynomial or functions with non-negative coefficients. So a polynomial function with non-negative coefficients must have non-positive 0. Okay. Now take a look at fx, which is I cubed minus I squared plus x minus 1. Then in this case, if you evaluate f at a negative real number a, then fa is always negative, meaning that a 0 of f need to be positive or 0. Okay, and in this situation we can also generalize this observation. So actually we call the coefficient of a polynomial function alternating if, so first of all, the coefficient of even power of x have the same sign, and similarly for the coefficient of odd power of x. And we also require that these coefficients have different signs, meaning that the coefficient of even powers must have different signs from the signs of coefficient of odd power bytes. So for example, in this case, the polynomial function 4 times x power 6 plus 2 times x power 4 minus I cubed minus I plus 1 has alternating coefficients, because the coefficient of even powers of x are 4, 2, and 1, right? And the coefficient of odd power of x are minus 1, minus 1, right? And okay, 0 of a polynomial function with alternating coefficients must be non-negative, right? This can be argued similarly to the situation of the polynomial function x cubed minus I squared plus x minus 1, as we've seen before. Now we talk about Descartes' rule of size. The standard form of a polynomial function, we call that it is actually the form where we omit terms with 0 coefficients, meaning that we will not write any terms where the 0 coefficient appear. Okay, and a variation of size of a polynomial function written in the standard form is the location when the two consecutive coefficients change their sign. So for example, in this case, here the coefficient of x cubed is 4, but the next coefficient of x squared is minus 1. So the sign change from plus to minus. And in this polynomial, there's only one variation of sign. So the Descartes' rule of sign states as follows. The number of positive real zeros of a polynomial function f is equal to the number of variations inside of fx minus an even integer, and the number of negative real zeros of f is equal to the number of variations inside of f of minus x minus an even integer. So for example, here in this case, because fx has only one variation of size, then it has one positive real zero. So in this case, because there is no even number between 1 and 0, so fx can have only one positive real zero. And now if you want to talk about the number of negative real zero, you have to compute f of minus x. And in this case, we see that f of minus x have actually 3 variation of signs. So for this reason, we see that f might have 3 or 1 negative real zero. Okay, so at least we can tell that f has exactly 1 positive real zero, and it has at least 1 negative real zero, meaning that it will have at least 2 real zeros. Descartes' rule of size somehow has these limitations. So first of all, it's only give us an estimate to the number of zeros, meaning that, well, if fx has variation of size, then we can only tell that it might have 8, might have 6, 4, 2, or 0 positive real zeros. And we can't even tell whether f have actually a positive real zero or not, because we might find the situation where f has no positive real zeros. But however, if fx have an odd number change in size, then we know that at least f have a positive real zero. And similarly for the situation where f minus x have an odd number of changes in sign. Okay. The second limitation is that the Descartes' rule of sign counts multiplicities, meaning that if one zeros have multiplicity 2, then Descartes' rule of sign would count this at 2 zeros. Now, there is a way to find potential zeros of a polynomial functions. Well, very often polynomial functions are given with rational coefficients, or maybe even more convenient, more conveniently, f will have integer coefficients. So in this case, we can ask whether f has a rational 0 or not. This is the criterion for a rational number p over q to be the 0 of f. So suppose that the greatest common divisor between p and q's is 1, meaning that they are co-prime. Then if f of p over q is 0, then we must have that p is a divisor of the constant coefficient a0, and q must be a divisor of the leading coefficient an. So for example, given the polynomial function as following, then the possible rational zeros of x are actually plus or minus 1 over 1, plus or minus 3 over 1, plus or minus 1 over 2, and plus or minus 3 over 2. This comes from the fact that 1 and 3 are actually divisor of 3, and 1 and 2 are actually the all divisor of 2. So by simplifying this, we get plus 1 or minus 1, plus 3 or minus 3, plus or minus 1 over 2, or plus or minus 3 over 2 as potential rational zeros. So we are left with the problem of determining which are zeros of f of x, meaning that we have to evaluate f at each of the possible value here. So, by definition, a way to do that is actually substitute x by each of the potential number, and then try to compute all of the power of x, and then using addition to add one of the resulting numbers. But however, a polynomial function might have high degrees, and it's very difficult to do so. So we have, unfortunately, we actually have a better way to evaluate the polynomial functions at a specific number. That is content of syntactic division. Now say for example we want to compute f of 1 over 2, then actually there is a very important observation that if r is a remainder of the division of f of x by x minus 1 over 2, then r is exactly the value f of 1 over 2. So the problem of evaluating f at 1 over 2 is the problem of finding the remainder of f by when we divide f by x minus 1 over 2. So let's see how we do that. Okay, so remember we can make long division. If you want to divide the left polynomial by the one on the right, then you take the highest coefficient, highest term of the left, and divide it by the highest term on the right. Then you get 2 times x cubed, and then you multiply this term with this thing here, the divisor, and then you get this polynomial. Taking the difference between these one, you get another polynomial. And you do the same trick again with this one. Now replace the dividend here, and then you get the second terms of the quotient. Do the same trick. Then here you get another polynomial which will give us the third term of the quotient again. So this one will actually give us the constant coefficient of the quotient. And again, now we comes to the remainder, meaning that f of 1 over 2 is actually this value, minus 45 over 8. Okay, but actually we promise an easier way to compute f of 1 over 2, or at least not as long as this one. So here's the division is actually long because it's contains a lot of things that is not that are not relevant to the problem of finding the remainder. So now let's take a look at how we can get rid of the irrelevant actually, in order to compute the remainder of the division, so we see that the appearance of the power of x is not necessarily is not mandatory, right? So instead of writing all the terms of the polynomial, we can write first the number we want to evaluate, followed by all the coefficients of the polynomial f. And look, the first coefficient of the quotient is actually 2. It is actually the coefficient of the highest, the leading coefficient of f of x, right? So we can transfer it down to the third line. So we know that this is actually the number here. What about phi here? Phi here is actually 4 plus 1 or 4 minus 1. And what is the coefficient 1 here? 1 here is actually the multiplication of this thing and this thing, meaning that you take the multiplication of this one and this one, then you will get the next thing you want is 1, and then you take the sum of this, you get 5. Okay. So what about this? This is actually the sum of minus 1 here with 5 over 2. Okay. But 5 over 2 is just a multiplication of this one and this one. And then by multiplying this, we get 5 over 2, and taking the sum of these on the same column, we get 3 over 2. And say, multiply this one with this one, you get 3 over 4. Take in the sum, but minus 6 and 3 over 4, you get minus 21 over 4, which is actually the constant term of the quotient, right? And similarly, if you take the same thing, here you have minus 1 over 8, which is minus 21 over 4 times 1 over 2. And if you take the addition of these two numbers, you actually get the remainders. Okay, so that is how you can use only the coefficient of fx and 1 over 2 to produce the coefficient of the quotient and also the remainders. This is called synthetic division, and this is called the third line or third row of the synthetic division. And from this we deduce that f of 1 over 2 is actually minus 45 over 8. And now with the help of synthetic division, not only we can compute f of any number n, we can actually give a criterion for upper and lower bounds of 0, similar to the one we've already seen previously. Now, let m be a positive number. So, if the third row of the synthetic division of f of x by x minus m contains only non-negative numbers, then f is an upper bound of the 0 of f of x. So, that is not very difficult, and if you pause the video for a little while and take a look back at the case where we show that a non-negative coefficient polynomial has 0 as the upper bound, then you can easily see that this assertion holds. And similarly, if m is a negative number, if the third row of the synthetic division of x by x minus m contains alternating numbers, then m is a lower bound of the zeros of f of x. So the last technique about finding 0 of polynomial function f(x) is the so-called intermediate value theorem, meaning that for a polynomial function f(x), if we can find two distinguished or two different real numbers, a less than b, such that the product of f(a) and f(b) is strictly negative, then we know that there should be some 0 between a and b. So for example, look at this function. Now we will try to compute f1 and f3 over 2, then trying to use the intermediate value theorem. So now we want to use synthetic division to compute f1. So we write 1 on the left and followed by all the coefficient of f. And so the second row can be computed as follows. We take the product of 1 and 2, right? And you have 4. the sum of 4 and 2, you get 6, and you take the product of 1 with minus 1 plus 6, you get 5, and the last thing, you do the same thing. You take the number minus 6 and 5, you take the sum of them, and multiply by 1, and you get minus 1. So now, column-wise, you take the sum of every element in the same column, and you get the third row, meaning that the remainder now is minus 4. Okay, so f of 1 is minus 4. And similarly, you can compute that f of 3 over 2 is 75 over 8. So the value of f1 and f of 3 over 2 has different signs, meaning that f should have 0 between 1 and 3 over 2. Okay. So that is how we can use intermediate value theorem to actually determine where the f should have a 0. Now let's finish the video by a specific example where I can show you how to use the technique that we learned so far in order to determine the zeros of these polynomial functions. So first of all, look at the coefficients of the polynomial. You have 2, 4, minus 1, minus 6, and minus 3. Then the Cauchy bound of this polynomial is actually 4, meaning that every zero of this function should lie between minus 4 and 4. And from the leading coefficient 2 and the constant coefficient minus 3, we know that possible rational zeros are plus or minus 3, plus or minus 1, plus or minus 3 over 2, or plus or minus 1 over 2, and the corresponding x-intercept of possible x-intercept of the graph on the x-axis are given here. Right. So the problem now is that we have to first of all try to evaluate f at these values. But before that, we actually have the Descartes rule of signs, right? So for there is only one variation of sign here in fx, then you know that they are exactly one positive with 0. And also for x minus x have 3 variations of sign. Then we know that f of x might have 3 or 1 negative with 0. So because we already know that f of x have exactly 1 positive real 0, we can start with trying to evaluate f at the least possible rational 0, meaning that we want to evaluate f of 1 over 2 using synthetic division. We already done that, so we know that it is minus 45 over 8, so this is 1 on the graph, meaning that 1 over 2 is not a 0, so we proceed with 1. So f of 1 is equal to minus 4, right? So it is not a 0 of f. And also from the third row, we cannot tell that 1 is the upper bound for zeros, right? So we proceed with 3 over 2. Well, for 3 over 2, then f has a value of 70 over 8, 75 over 8. This is not a 0 either. However, we know that when we pass from 1 to 3 over 2, then the value of fx change the sign, meaning that we should have 0 between 1 and 3 over 2. So from now we can conclude that f should have a irrational 0 here, somewhere between 1 and 3 over 2. And we don't need to to evaluate f at 3, because we know that f has only 1 positive 0, right? So now we can turn our attention to the negative possible 0 of f. Now, f of minus 1 over 2 is minus 5 over h, right? So it is not 0. And from the third row of this division, we cannot tell whether this one is a lower bound for 0 of f or not. So we proceed by computing f of minus 1. Oh well, so in this case, we already get 0, meaning that minus 1 is actually a 0. Okay, it's good. So because minus 1 is already 0, and we know that there's might possibly be 1 or 3 negative 0 of f, right? So we can ask whether the multiplicity of minus 1 is 1 or more. So for that reason, we can actually now factor f of x as x plus 1 multiplied by gx like this. And we use the symplectic division again to get x plus 1 out of this if possible. And actually g of minus 1 is 0, 2. So for this reason, we see that the multiplicity of minus 1 is actually more than 1. This might be 2 or more. Well, but we can easily check that from this minus 1 is actually a multiplicity 1 of g, meaning that it is actually a multiplicity 2 of g. And we also have fx equal to x plus 1 square times 2 times x squared minus 3. And from this, we can easily deduce that all the 0 of f of x are actually minus 1 with multiplicity 2 and plus or minus square root of c over 2. And this is how the graph of f looks like. And this is actually how we can determine all the zeros of f.